Welcome to the Problems Channel Season 3, Episode 22, the episode which I titled A Planar Motion with a Constant Non-Zero Tangential and a Constant Non-Zero Normal Accelerations, because in this episode we will recover the shape of the trajectory traced by a point that executes the motion in a plane in such a way that its tangential acceleration remains constant and non-zero at all times, and its normal acceleration remains constant and non-zero at all times. But before we deep dive into the underlying mathematics, as a traditional and friendly reminder, if you're joining our channel mid-season, then first of all, thank you very much for your vote of confidence. Thank you for subscribing to our channel and welcome to our channel. And second of all, perhaps the most efficient way for you to gain the most academic benefit for yourself from working with the material that we present on this channel is for you to go to the homepage of our channel, and in the trailer section at the top portion of that page, find the episode titled The Problems Channel How To. We recommend that you watch that episode in its entirety, follow all the instructions that we give in that episode, because in that episode we explain and motivate everything that we do on this channel. If you have any questions, then by all means do ask. The best way to ask your question is to find an episode on this channel that is of interest to you and use the comment section under that episode, and I will take it from there. And of course, I would like to extend my deepest gratitude to all the current subscribers and the current supporters of our channel. In the physics problem S3E22, we're told that a point executes a motion in a plane in such a way that at all times its tangential acceleration remains constant and non-zero, and its normal acceleration remains constant and non-zero. Under these conditions, we are required to recover the shape of the point's trajectory. As a fun experiment, in order to test your intuition as a theoretical physicist, we recommend that before we generate the solution of this problem, you pull up a piece of paper, write down your name on that piece of paper, write down the date, and write down your fearless prediction. What do you think, intuitively speaking, before deep diving into the underlying mathematics? What is the shape of the trajectory traced by the point in this problem? As a hint, the name of that curve is very well known, and I'm pretty much sure that you have heard about it. Now, in Season 2, Episode 51, I'll write it down for you over here. In Season 2, Episode 51, we explained how to solve problems in physics in general, and that template is quite straightforward. We begin with the spoken language, whatever your native language is. Then we translate that spoken language into the language of physics. Then we translate the language of physics into the underlying mathematics. We deal with mathematics, we fight the mathematical fight, we solve the mathematical problem, and then we start the reverse process of translations. From the language of mathematics, we translate the result into the language of physics, and from the language of physics back into the plain and spoken English. In this problem, the situation is very straightforward. We're told that the tangential acceleration, we'll designate it with a tau, where tau designates tangential, remains constant and non-zero at all times. We know that captured in its natural coordinates, the tangential acceleration will be the second time derivative of the length of the curve as traveled so far. So this will be a real number, a. It will not be 0. It remains constant, and a belongs to the set of real numbers. We're also told that the normal acceleration, which is captured v square over the radius of curvature, so it will be s dot, the first time derivative, squared divided by r, where r is the radius of curvature of the trajectory at that point, it is, let's say, a constant non-zero real number as well. So we write it down as follows. B also belongs to the set of real numbers. And now the objective is to start with these two relations, and from these two relations extract the shape of the underlying trajectory. These channels' regular customers, and especially the folks who know me from Quora, already know that back in my time, all the examinations in theoretical physics, mathematics, and computational sciences were carried out in the real-time, face-to-face format, where you walk into the auditorium, you give the, let's say, theoretical physics professor your name. He or she will write it down on the separate piece of paper. Against your name, there will be the number of the ticket or list of problems that you have to solve. You'll be given 15, 20, maybe 30 minutes to compose yourself. And then you'll step up to the plate and tell the story. Because remember, in season 1, episode 1, we told you that mathematics is an art of telling a story. Well, physics is pretty much the same thing. It's also an art of telling a story. In this case, the story unfolds as follows: from the fact that the tangential acceleration of the given point that executes the motion in the plane remains constant and non-zero at all times, we have this, a very pleasant ordinary differential equation. If you've been watching our episodes that we put together during the season number 2, you already know how to solve this type of equations. This is called an equation with separable variables. So we separate the variables in this case as follows. First, we spell out the definition of the second time derivative of the mystery curve S. In other words, from here it follows that ds dot over dt is equal to a. We multiply both sides of this equation by the single copy of the first differential. In other words, ds dot over dt times dt is equal to a times dt. We cancel out the first differentials of time on the left hand side of the equal sign. From here we have ds dot is equal to a times dt, and from here it follows, what do we do next? What is the next tactical maneuver? We multiply both sides of this relation. Let's write it down. Multiply by a single copy of the first time derivative of s. This is a way to separate the variables in this case. And what do we have? We have s dot times ds dot is equal to a dt times s dot. Here we leave the left hand side of this relation as is. We do not touch it. We massage the right hand side as follows. We spell out the definition of the first time derivative of the mystery curve S, and we obtain a dt times ds over dt. The first time differentials cancel. We have a times ds. We now take the left hand side of the equal sign, the right hand side of the equal sign, and we have s dot ds dot is equal to a ds. What is the next maneuver? You are right, we integrate both sides of this relation. Integral, and we carry out the integration in the definite sense. On the left hand side, we integrate from the initial velocity s dot 0 to the current one s dot, and on the right hand side we integrate from the initial position on the mystery curve s0 to the current one. The integrals over here come out less than trivial. We have on the left hand side s dot squared over 2 evaluated between s dot 0, the initial velocity, and the current one, and this is equal to, let's write down this result right away, a times s minus s0. From here, it follows that once we spell out this construct over here, we will have the square of the current velocity minus the square of the initial velocity is equal to what? 2 in the denominator of the left-hand side. We move into the numerator on the right-hand side is equal to 2a s minus s 0. And lastly, we can take the constant term in the result of this integration and move it from the left-hand side to the right-hand side. In other words, we obtain the following relation. S dot squared is equal to the square of the initial velocity plus 2a s minus s0. This is one result that we deduced in an expedient fashion. Let's say you want to call this the relation number 1. Observe that in the relation that we just deduced, what do we have on the left-hand side? We have precisely the square of the point's velocity. And what does that mean? That means that if we divide it by the radius of curvature of the mystery curve at that point, we will have precisely what? We will have precisely the magnitude of the point's normal acceleration, which remains constant, non-zero real number b at all times. Consequently, if we swap r and b, let's say we will yank it like this so you can see the trace, but now we exchange b and r by a very straightforward maneuver. Now we recall the rudimentary differential geometry 101, which you're expected to know at this point in your theoretical physics career. You know that the radius of curvature is given, for example, by ds over d theta. You know what s is. S is the length of the curve traveled so far by our point. And what is theta? Theta is the angle that is formed by what? Is the angle that is formed by the positive direction of the straight line that is tangent to the given trajectory at a given point, and the positive branch of the x-axis in a particular chosen Cartesian coordinate system. That much you know. And what does that mean? That means that over here, if we glue this expression to this expression, we have another beautiful relationship in which we can separate the variables one more time as follows. All the material that pertains to s we collect on one side of the equal sign with the first differential ds, and d theta we isolate on the other side, where evidently we only have the inverse of b, and that is why also, among other things, we require that b is not equal to 0. If we rewrite this relation as follows, ds divided by s dot squared 0, the initial velocity, plus 2a s minus s0, it will be equal to 1 over b d theta. Again, one more time, we want to understand what the symbol theta stands for. It's the angle formed by the positive branch of the x-axis in a chosen particular Cartesian coordinate system. Origin, scale, the unit of length on one side, on one axis, on the other, and the positive direction of the straight line that is tangent to the given trajectory. This is our curve S at the point, at the location, at the current location of the point. What do we do now? Again, we integrate. We integrate on the right-hand side from the initial angle between the tangent to the trajectory and the positive branch of the x-axis to the current one. And on the left-hand side, we integrate between, again, the initial position on the curve as 0 and the current one. The integrals on both sides again come out to be trivial. There is nothing to write home about in this particular case. You should be snorting this integral with your left nostril with zero effort. Over here, the whole thing can be moved under the differential, and the only thing we need to accommodate or account for is the factor of 2a. So once we move the denominator under the differential, we have to divide the whole thing by 2a. In other words, from here, it follows that 1 over 2a log the natural logarithm or the logarithm in base e. Let's write down the expression right away. What will it be? It will be the expression shown over here evaluated at the upper boundary, which will be the square of the initial velocity plus, what is it, 2a s minus s0 divided by what? Divided by this expression evaluated at the lower boundary, s0. s0 minus s0 eliminates this term. The only constant term survives over here, so we have s dot square 0, and this equals to what? 1 over b. Let's write it down this way: theta minus theta 0 over b. Now, once we move the reciprocal of 2a from the left-hand side to the right-hand side of this relation and potentialize it, what will happen? Well, what will happen is the following: s dot squared plus 2a s minus s0 will be equal to what? S dot square 0 times e raised to the power of 2a over b theta minus theta 0. This maneuver should be understood by everyone in the audience. There is nothing complicated over here. This is just baby or middle school arithmetic. Now, we have a constant over here that's lurking in the midst of this material, which is the base of the natural logarithm, e raised to the power of 2a over b minus theta 0. In other words, we rewrite this expression as follows. This will be the square of the initial velocity times e raised to the power minus 2a over b theta 0. You see, this is a constant term, times e raised to the power of 2a over b theta. Now, this thing over here is a constant, so we rename it as k for a constant. This is a constant real number, and that means that we have the following relation: some constant times exponent e raised to the power of 2a over b theta, and that is equal to this expression. So let's glue everything together. What do we have? S dot square 0 plus 2a s minus s0 is equal to k times e raised to the power 2a over b theta. This is our other relation that, if you want to number it, let's say that will be number 2. As I was reviewing the footage of the previous segment, I realized that I made a small typo, so I apologize to my audience. Literally a few seconds ago, in one of the intermediate deductions towards the end of the previous segment, I forgot to put the index of 0 with along with the square of the first derivative of the curve s, and that is important, and we will see why in a second. Yet another knowledge of differential geometry that you're supposed to demonstrate during the solution of this problem is the following. If we project the infinitesimally small arc s onto the chosen x-axis, then we will have the following relationship: cosine theta ds, and the same relation, a similar relation, holds for the projection of the infinitesimally small arc of the curve S onto the y-axis. This is differential geometry 101. I will not be deducing it. In some sense, you should be able to deduce it on your own. You come up with a finite or small segment of the curve. You construct a triangle, and then you execute the limiting process when two seconds merge into one, they become tangent, and this is the relation that we have. And this is where the importance of this subscript over here becomes relevant in the expression number 2. Here we take the first differential ds of both sides of this expression shown over here. Remember, this was our expression number 2. We marked it as number 2. And if we take the first differential of both sides of this relation, then we will have what? The first differential of a constant, 0. Constant, 0. So what do we have left? We have 2a ds on the left-hand side. And what do we have on the right-hand side? On the right-hand side, we will have the following. 2a in the numerator over b in the denominator times k times the exponent itself, 2a over b theta d theta. You see, it is that straightforward. What do we see here? 2a and 2a on both sides cancel out, and look at this wonderful construct we have. For the first differential ds of our mystery curve S, we have k over b times e raised to the power of 2a over b theta d theta. And now, if we put this expression over here and over here, we will obtain the following two expressions. For dx, it will be, let's take the constant out right away, it will be k over b, then e raised to the power of 2a over b theta times the cosine of theta d theta. And for the coordinate y, we will have a similar expression, k over b e raised to the power of 2a over b theta, but this time we multiply by what? We multiply by the trigonometric value of the trigonometric function of sine of theta. And now what will we do? Well, now again we integrate, but this time we're almost done. Normally we have a choice. We can integrate in the definite sense or in the indefinite sense. When we integrate in the definite sense, we need to put the boundaries from, let's say, x0 to x, from y0 to y on the left hand side. On the right hand side, we will integrate from theta 0 to theta again, and here the same thing, from theta 0 to theta. But because essentially we will see in a second that this will pile up the let's say arithmetic complexity, and it will only muddy the waters. Here we will carry out the integration in the indefinite sense, and then we will execute the following maneuver. The plus c in both cases, the constant of integration, we will set to 0, and by so doing, and I'll explain it in a second again, by so doing we will fix a certain Cartesian coordinate system in the plane of the motion of our point. And this is not a crime, this is perfectly valid. But before we do that, the reason I wanted also to solve this problem is to show the students that in, let's say, calculus or real analysis or mathematical analysis or whatever else this course will be called in your country, basically the place in the study of mathematics where you deal with integration. In this text, you will see all sorts of wonderful integrals, and the question that students frequently have is the following: where do these integrals come from? Well, here we see that some of these integrals come in a beautiful fashion directly from physics. And here we will show that this is the case precisely by integrating both of these relations. So we'll integrate this relation in the indefinite sense, and we will integrate this relation in the indefinite sense. And because this is a constant, we will move it out from under the integral sign. This is a constant. We will move it out, and look at this. We will have a pair of integrals that are basically nothing but ubiquitous, and we will take for now a strictly utilitarian approach to these integrals. We will take them as a previously solved problem, and if you want to see how these integrals can actually be evaluated, we will evaluate these integrals in a creative way in 3 different ways in season 3 episode, what is this, 22, 23? This will be episode 24. So this is the episode to watch. We will evaluate these integrals in 3 distinct creative ways using the complex numbers, constructing a system of linear equations, and then using ordinary differential equations to evaluate this integral. But for now, like I said, we will take a strictly utilitarian stance, and we will treat these integrals as a previously solved problem. All jokes aside, the integrals that you just saw are actually quite epic. You will see them on this channel on and on and on again, especially when we come to the integration of the so-called improper integrals over infinite set of real numbers. And the reason I gave the arguments to of the exponential and the trigonometric functions, the parameters p and q, in order to avoid the confusion with a and b over here. Usually we carry out this integration with the constants a and b, and the maneuver that we execute right now is straightforward. For the parameter p that you just saw, we put 2a over b, because precisely this is basically in the integrals you just saw is p, and for the q, for the parameter q, you put equals 1, and we obtain the following results. One more time, in the community section on this channel, I gave a fair warning and a fair heads up to the curious viewers. I told you that you will be able to find out where do the integrals in your favorite calculus, real analysis, or mathematical analysis textbook come from, and now you know, you've heard it here. Among other things, these beautiful integrals come precisely from physics. And if we carry out the substitutions that I already explained, we put 2a over b equal to p. In the previous formulas that you have seen, we put q equal to 1. Then our integrals that we will again zoom in great detail in season 3 episode 24 come out to be equal to this expression for the coordinate x, this expression for the coordinate y. Consequently, we will have x equal, we will have y equal, x of theta, y of theta. Again, what is theta? Theta is the angle formed by the positive branch of the x-axis in the positive direction of the straight line tangent to the trajectory of the point at its current location. And as I promised, specifically, I put plus 0 for the constant of integration, plus 0 for the constant of integration. Here you should be able to see the following, that if we were to carry out definite integration, what would we have, for example, on the left hand side over here? We would have had x minus x0 equal to, we would have had this term over here minus, this is a constant, this term raised to the power theta 0, theta 0, theta 0. It would have been another constant. And what does that mean? So it means that if we were to say again x equal to this expression plus x0 plus another horrible term that looks like this with the theta 0 all over, it only means that our initial coordinate in the chosen Cartesian coordinate system would have been this. But instead of doing all this, again, you're more than welcome to carry out this experiment. There is nothing fundamentally interesting or important that in some sense we're losing here, if you will, just by setting the constant of integration to 0 in both cases. All we're saying is that we are putting all these initial values of x and y, we're setting them to 0, and by doing so we are choosing or fixing a particular Cartesian coordinate system in which our point executes its motion. And now the question is, how can we wrap our brain around these trigonometric material laced formulas, and how do we name the trajectory that our point traces under the conditions specified? When I was writing on Quora, I have seen my fair share of questions from younger students that went like this. I want to do theoretical physics, but I don't think that my mathematical abilities are that high. Well, the answer to this question is the following. What do you want first, the good news or the good news? Here, the first good news is that in this day and age, I do not really see how anyone can succeed in getting even the bare minimal degree in theoretical physics without being able to hold his or her own in mathematics. And the truth of the matter here is that every, let's say, full-time theoretical physicist is a mean part-time mathematician. The converse of the statement is not true. It is not the case that each and every full-time mathematician is a mean part-time theoretical physicist. Maybe that have been the case 300 or 400 years ago. And for example, Isaac Newton and Leonard Euler were typical representatives of both mean mathematicians and mean theoretical physicists. Now, the other part of the good news is that you made the right choice by coming to this channel. On this channel, we will give you a realistic sense of your mathematical prowess that is expected from you if you want to succeed in earning a degree in theoretical physics. I obviously do not crank up the level of rigor and intensity at which I was studying back in the day, but like I said, again, you will get a realistic and representative sense of what is expected of you in terms of your mathematical abilities and your mathematical prowess. Because let's say, just like Isaac Newton or Leonard Euler, you want to tell the story to the world of a point traveling in the plane in such a way that its tangential and normal accelerations remain 0 and non-constant at all times. What is the name of this trajectory? You went this far in the solution of this problem. You now arrived at these two beautiful expressions. You stare at them. What is your next maneuver? What would you do at this point? You see, at this point, this is nothing but mathematics, and precisely the creativity, your ingenuity in mathematics is what is needed from you over here. And in some sense, in a properly constructed or in a properly put together theoretical physics curriculum, the corresponding mathematical curriculum runs at least one, hopefully two or even three semesters ahead. In other words, when you study theoretical physics, you always want to know more mathematics at that time. So here in your real analysis course, you may have remembered that you were either asked to prove as a homework assignment, or maybe the lecturer proved it to you during the presentation of the course during a lecture, that every continuous and monotonically increasing, let's say, or decreasing function, or let's say a map, has the converse that is also continuous and is monotonically increasing or decreasing, as the case may be. Back then, when you were looking at this theorem back in your real analysis course, you probably thought, oh, gee, yet another theorem. So what? Well, here you will need this information precisely, and that is, again, the manifestation of the fact that every theoretical physicist is a mean part-time mathematician. You need to be able to yank from your personal web of mathematical knowledge the right unit of mathematical knowledge when you work in theoretical physics. So here you will take your favorite trigonometric function let's pretend this is plus pi over 2 and this is 0, and let's say this is minus pi over 2. The vertical asymptotes, what is this? What is this graph? Well, you know that this is the graph of your favorite function, tangent of theta. Of course, it has many branches, shifted to the right, shifted to the left, but we're only interested right now in the principal branch. This function is continuous and is monotonically increasing. Let's say if we agree that the corresponding values for the argument, the numbers that come from the subset of real numbers from open subset minus pi over 2 to plus pi over 2 grow in this direction, then consequently the values of this function grow. And what does that mean? Well, that means that no matter what real number we pick or think of, let's say this one, let's say the real number rho 0, or this real number right here, rho 0, for each such number, in other words, we can even throw some more mathematical rigor into it, for any real number rho whatsoever, there always exists another real number alpha 0 that belongs to, well, it is a real number from the subset of minus pi over 2 to plus pi over 2, such that rho is precisely the value of the trigonometric function of tangent evaluated at this real number. In other words, we always have some, let's say, angle alpha 0, and here we'll have some angle 0. In other words, we can think of the trigonometric function of tangent as taking this open, or let's say small, subset of real numbers, and then this function unzips or uncompresses them into the entire real number. In this case, the vertical axis y that captures the values of this function represents the entire set of real numbers. Its inverse you already know also, and now this will be plus pi over 2, this will be minus pi over 2, like this, and your arctangent will run like so. And in this sense, this function does the opposite. It takes the entire real number line, let's say, or the entire set of real numbers, and compresses them into this here subset of real numbers. And for us, what that means, all this mathematical, or let's say real analysis mumbo jumbo, what that means is that this is very relevant to us over here. What do you think we will do right now? Well, right now we will claim the following. Look at this. 2 is a finite non-zero constant real number. A is a finite non-zero constant real number. Their product is a finite non-zero real number. B is a non-zero constant real number. So the ratio of two real numbers, the denominator of which is not zero, is yet another, in this case, constant non-zero real number. This is exactly the real number rho, sits somewhere over here, and that means we can always put it equal to the tangent of some angle alpha 0. We do not really care what this value is. All we care about is that we can do it, all courtesy of the corresponding theorem from real analysis. Now what do? Well, look at this. Look at what we have for the expressions x and y. And at this point, you tell me what the next maneuver is. Now that we have defined the trigonometric function of tangent evaluated at the angle alpha 0 as our ratio 2a over b, 2a over b, 2a over b, 2a over b, let us work, let's say, with the expression for x. First of all, 1 divided by tangent square plus 1, 1 divided by tangent square plus 1. What is this? This is nothing but middle school trigonometry. This will be cosine square of alpha 0. Would you agree? 1 divided by tangent square of alpha 0 plus 1. T over here is my shortcut for this animal right here. This is it. Middle school arithmetic, zero intellectual effort. So for x, let's say I'll put roughly, I will drop this exponent over here. We do not need it. So what will we have? We will have cosine square of alpha 0 times tangent of alpha 0 times the cosine. Let's spell out the tangent. That will be what? Sine of alpha 0 times the cosine of theta plus cosine. So we will write down cosine of alpha 0. This is our tangent. Plus, we need to multiply this guy right here. Cosine of alpha 0 times the sine of theta. What do you see? One copy and one copy of cosine alpha 0 cancel each other out. And what do we have over here? Sine times cosine plus cosine of the first angle times the sine of the second. Well, that will be, we have one copy of cosine. Let's do it this way, cosine of alpha over there. And this is expression, it's a synonym for the sine of the sum of theta plus alpha 0. You see, this expression over here, this plus this, is the synonym for the sine of the sum. So far so good. Now let's look at the expression for y. For y we will have the same thing, 1 over tangent square plus 1. So we will have the cosine square of alpha 0 times, but here we will have what? Tangent of the angle alpha 0 times the sine of theta minus, over here, don't forget we have a minus. So here we'll do the same exact maneuver. We unzip the trigonometric function of tangent according to its middle school definition, sine divided by the cosine. We bring everything under one denominator, and what do we have? We have sine of alpha 0 times the sine of theta minus cosine of alpha 0 times the cosine of theta divided by the cosine of alpha, again square, one copy goes out. Here we have cosine of alpha 0 times what? You tell me. You need to be careful over here because sometimes students lose this negative sign, but this expression over here, if we factor 1 out, will be cosine cosine minus sine sine. So what is this? This is minus 1 times the cosine of theta plus alpha 0. Don't forget the minus over here. This is important. We do not want to lose it. So you understand this abbreviation that I used over here. I simply drop these two constant factors over here. Constant in which case? Well, we're working right now with this guy. We want to fold these expressions into something manageable. And now that we understand the genesis of these expressions over here, this one and this one for the x and y, we can write down this expression over here in a more official form as follows. And if we carefully carry all our intermediate computations through and write down the expressions for the x and y coordinates as the function of the angle theta, which we remember is the angle between the positive branch of the x-axis and the positive direction of the straight line tangent to the mystery curve at the current location of our point, then we will have these two expressions. I will not comment on them. Everything is defined and understood over here. exp is what we use in mathematics to write down the exponential function, so it's just convenience for the purposes of saving the real estate. We do not need to put the towers of powers. And we define the angle alpha in such a way that the value of the trigonometric function of tangent at that angle is 2a over b, or twice the ratio of the tangential acceleration to the normal acceleration of our point, and the constant k is expressed over here as basically a collection of another bunch of real numbers. And we're home free in some sense. Maybe some of our viewers who are deeper in mathematics than I am may already recognize the shape of the trajectory that is traced by the point. In this case, this is a logarithmic spiral. But those of our viewers who do not travel that far into, let's say, differential geometry and cannot tell the shape of the curve when we have two expressions shown over here, x and y. Again, this is purely a mathematical maneuver, and this is again comes back to my earlier statement that every theoretical physicist is a mean part-time mathematician. You need to be able to hold your own in mathematics in order to succeed in theoretical physics, or in order even to have a chance at succeeding. So what do we do here? We introduce the polar coordinate system where, let's say, we take one point O, which is the pole. We take one straight line in arbitrary direction, that is the polar axis. And then in the this is taken to be positive direction. We need to set the scale. Let's say this is 1 unit or whatever of distance. And then any point in such a system, the point P, will be characterized by the length of its radius vector. We need two real numbers in the plane. We can also construct a polar coordinate system in 3 space. Here the motion is, where is it? Motion is planar. 2 space is enough. So 2 real numbers r, and another one is, let's say, phi. We want to be sure that this is not technically our angle theta over here. Remember, tangent, polar angle, tangent, tangent, polar, polar, tangent. Did that make this painful enough for you? Okay, very good. So this is my point. So now how do we connect the polar angle phi to our tangent angle theta? Well, the maneuver here is the following. First, let's compute r. What is r? R is, in this case, in general, it will be a non-negative real number, but in our case, we're interested in positive real numbers, so that will be square root of x squared plus y squared. And in this case, what this number comes out to be, look at this beautiful stuff. Constant, the same exact constant with the minus sign, square, square, carried out, sine squared plus cosine squared collapses into what? Into the positive unity. And once we extract the square root of this whole caboodle again, what do we have? Well, we have precisely this expression, k over b times the cosine of alpha 0. This time I'm collecting all the constant material on one side, and now we have, if you will, okay, I'll use the notation that probably more students are used to. Instead of this, this is what you will see in complex analysis all the time. This will be 2a over b times theta. This is our result. So the radius is this. But now how do we connect the angle theta to the polar angle phi? Well, remember that for the polar angle phi, what can we say? The magnitude of this angle can be computed via the trigonometric function of tangent. Again, our favorite tangent. This is what? This is technically y divided by x, and in this case it's the other way around. The constant cancel out, and then we have what? We have the what do we have? Y over x. We have the cotangent, right? Cosine divided by the sine. Cotangent of theta plus alpha 0, and with the exception that, of course, as much as I was telling you guys to not forget it, I obviously forgot it. So the minus sign, so it's minus cotangent of theta plus alpha 0. Now, what does it mean? Again, you put on the head that says a mathematician. So for any beta real, it is the case that the cotangent of beta plus minus pi over 2 is equal to tangent of beta. This is the basic mathematical fact that you carry in your bone marrow somewhere. And that means that from this tangent of the, look at this, the tangent of the polar angle is equal to the minus cotangent of this formation. So what does it mean? Well, from these two facts, it follows that our angle, polar angle phi is equal to the angle which is, we call it tangent, plus alpha 0 plus minus pi over 2. That means that the polar angle of our point that executes the motion in the plane in such a way that its tangential and normal accelerations remain constant and not zero at all times differs from the corresponding tangent. So here is some curve, and the tangent angle will be formed this way. This will be our theta. The difference between them is a constant real number. You see, constant. Alpha 0 is constant. We define it over here via two constants, and pi over 2 is 0. And that means once this maneuver is understood, we can bring our k that we defined over here and rewrite this expression as follows. Look at this. Let's do this. So this will be s dot squared 0 divided by what? b. And now we take the cosine, which is the square root of 1 over square root of what? 2a over b squared plus 1 times e raised to the power of what? 2a over b theta minus theta 0. You understand this, right? We took this, we put it into this expression over here for the cosine. The cosine, again, this is another middle school trigonometry that you're supposed to remember, is equal, in general, I think it goes plus minus 1 over square root of tangent squared of alpha 0 plus 1. So instead of tangent square, we roll back to our numbers. Basically, the idea is to unwind all our syntactic sugar, if you will, into the material that is given to us. Given, the initial velocity must be given. This also will be some initial angle, but look at this. Because of this relation, what can we say? We can say that theta minus theta 0 will be equal to what? Here we will say theta is equal to phi minus alpha 0 minus plus pi over 2. And that means that for the angle theta 0, we will have phi 0 minus alpha 0 minus plus pi over 2. So when we subtract theta, minus theta 0 will be phi minus phi 0 minus alpha, minus minus becomes plus, plus minus plus becomes, flips around. So basically that means that we have phi minus phi 0. You see this difference right here falls out that way. And once that all these maneuvers are understood, we can basically say that because of this, we can write down, let me erase this a little bit over here, you understand what's going on. So here we will have our expression phi minus phi 0. Let's erase this r over here and this, and we will have our r of phi like this. See, this is the expression in this form. Most students will recognize this. If we designate this with r0, then our trajectory expressed in the polar coordinate system will be recorded as follows. R of phi, the polar angle, is equal to r0 times e raised to the power 2a over b phi minus phi 0. And again, we can carry this constant roll it into over here. So basically, we will have our expression like this. Let's say rho 0, if you will. E raised to the power of 2a over b theta. So far, so good. Look over here. Let's say we'll define rho 0 is like this. R0 times e raised to the power minus 2a over b phi 0. That is another designation. This is it. So this goes over here. And in this form, most students should already see what is going on. This is a logarithmic spiral. I'll give you a chance to put this video on pause, record this, or take a good note. I will erase it. I will erase some material over here. I'll keep it up to here. I mean, these trigonometric contortions you should be able to carry out on your own. And at this point, you will remember that in general, a logarithmic spiral is given by the following expression: r in polar form as a function of phi, the polar angle, will be exactly this: r0 times a raised to the power k times phi. This is the logarithmic spiral. A is greater than 0. Of course, the interesting cases are a is greater than 1. This is our case. A is equal to e. Another case is a is less than 1. And if a is 1, then what is the logarithmic spiral becomes? Well, in polar coordinates, it becomes r0 is what? Origin-centered circle of radius r0. In our case, again, the strictly positive real number a is e. E is greater than 1. Everything is wonderful. This is our, what is k? K is this number right here, 2a over b. And once that is understood, here in the conclusion of this episode, I will say a few words. First, when I was a 19-year-old kid, when I was doing all this, it never ceased to amaze me that after we go through all these mathematical contortions, we still come out with something that makes sense. For example, look at how our mathematical manipulations led to the beautiful, for example, compression into this expression over here. And then where did this compression come from? Well, it came from this seemingly complicated integrals. E raised to some power times cosine or times sine. These integrals came out to something that eventually collapsed into this beautiful material. Everything worked out, and to this day, this still never ceases to amaze me how well mathematics works in conjunction with physics. That's on the one hand. On the other hand, I would like to say a few words about the definition of the so-called, if some of our viewers are familiar with this topic, curves of mechanical origin, where sometimes some curves can be defined in two different ways. Using a mechanical definition, for example, a trace of a point that sits on a circle and the circle rolls over another circle or along a straight line, then instead of a mechanical definition, we can give a purely geometric definition, analytical, for example, expression for this curve. But look at this. This time, we realize that if a point executes a motion in a plane in such a way that its tangential and normal accelerations remain non-zero constant real numbers at all times, then the point traces necessarily, as we just proved, a logarithmic spiral, not the, but a. And that means that it is also possible to define some of these wonderful curves, not from the geometric or mechanical standpoint, not analytically, but in terms of physics or kinematics, using the vocabulary of kinematics in terms of velocity and acceleration. You saw a perfect example of this here. Now, before I conclude our discussion of the problem S3EP5, look at this. There is lots of wonderful information that is associated with the logarithmic spiral. it goes like this, let's say, somehow. And the interesting thing over here is the following. Any straight line that passes through the origin of this coordinate system, through this number, you take this straight line, or this straight line, it doesn't really matter. Take the point where the straight line intersects our logarithmic spiral, construct a tangent to this point here or here, it doesn't really matter. The wonderful thing, or the wonderful property of every logarithmic spiral is the following. The angle between the radius vector and the tangent, tau, which means that the angle between the radius vector and the velocity of the particle that traces this. Let's say we measure it, I don't know, let's say this way, this our angle, alpha 0, let's say, will be the same always, will always be the same. This is alpha 0, and somehow we measure here, this will be alpha 0, and amazingly enough, it can be shown, again, using the apparatus of differential geometry, if you will, that the coefficient over here in the definition of the logarithmic spiral is nothing less and nothing more than the cotangent of this angle alpha. In other words, if we take the angle that is formed by the radius vector and the tangent to the logarithmic spiral at that point, then the value of the trigonometric function of the cotangent of this angle will be equal precisely to the factor in front of the polar angle k over here. And in our case, what is this thing? Well, our cotangent, maybe I chose a bad name, let's say we'll call it beta 0, beta, and beta, it will be 2a over b. Look at this, this is our coefficient in front of the polar angle, and in some sense, in addition to pure mathematically infused explanation of what is where, we also have now an interesting physics-based explanation that this, the associated angle between the tangent to the logarithmic spiral and their corresponding radius vector is explained through twice the ratio between the, what was A was the tangential acceleration, and B was the normal acceleration. And this is obviously not it. The logarithmic spiral has many more interesting properties, and you can think on your own. If, let's say, we step out from 2 space into 3 space, is it possible to construct a 3-space curve which has a dissimilar property? Think about this on your own, and for now, this is it for the physics problem S3P5, and we will move on to a new challenge next. Our next challenge will be a challenge in computer science, S3CS5, and I think it will be very, very cool because the emphasis of this challenge will be on writing a piece of software that animates and visualizes a particular algorithm, because in my humble and somewhat professional opinion, the animation and the visualization of computer science algorithms is a worthy task of its own. It can stand on its own in computer science, I think, and as far as I can tell, not much has been done in that direction, simply because we are very visual animals. I do not remember the exact numbers, but something like 80 or 85 or even 90%, some very large and substantial percentage of all information that we consume, let's say on a daily basis, comes precisely through the optic nerve in the visual form through our eyes. In other words, if we see how something works, we tend to better comprehend and understand how it works. So maybe I think it can even help animating and visualizing how computer science algorithms work, can help us not only understand better how the existing algorithms work, but it can help us invent new ones or improve maybe the existing ones. As such, the challenge of the computer science problem S3CS5 is first to explain in your own words how the so-called shunting yard algorithm works. That algorithm, not surprisingly enough, was put together by a person who was a theoretical physicist by training. That algorithm maybe is not very complicated, but is absolutely elegant, and in my opinion, it's quite mechanistic. The interaction between the stacks and queues is quite wonderful. And again, to me, it is not a surprise that such an algorithm was put together by a person who was trained as a theoretical physicist. This algorithm can be adjusted to do many different things. It's a little engine that it can be used to compute the values of arbitrarily parenthesized arithmetic expressions. It can be used to process arbitrarily parenthesized Boolean expressions based on strings. It can be adjusted to compute, let's say, derivatives of functions that are made of other functions, for example, decompositions, cosine of sine of tangent, feed it into the adjusted algorithm, boom, it will produce the, let's say, first derivative of this animal with respect to this argument and so on. So your first task is to explain in your own words how the shunting yard algorithm works. Read about this algorithm from your own sources. If you do not want to spend the time, I will explain how this algorithm works in the next episode, S3 episode 23. But the emphasis of this challenge is on the second task. Write a slow motion player that visualizes and animates and brings front and center the inner mechanics of the shunting yard algorithm. Use any software you like, share your ideas with us, post links to your GitHub repo. I will share with you my slow motion player of the shunting yard algorithm. I wrote it in Java back then. Java had a nice visualization library of its own, and this is exactly what I use. So this is it for this episode. Thank you very much for your time. Thank you for watching. I will see you in the next episode, in which I will explain how the shunting yard algorithm works, and in which I will share with you my version of the slow motion player of the shunting yard algorithm.